Welcome to Understand the Math. In this video, I'm going to walk you through exam questions on eigenvalues and eigenvectors. I'll summarize the step needed to solve each question and carefully work through every detail so that you feel confident tackling these problems on your own. Let's get started. In this question, we're given a vector v, and we're asked to find if it is an eigenvector of matrix A. And if it is, we're asked to find what the eigenvalue is. The way that we're going to solve this problem is we're going to check if A times our vector v is equal to lambda times v, where lambda is an eigenvalue. This equation is our basic definition of an eigenvector v and an eigenvalue lambda. Let's begin by writing down our matrix A. Minus 4, 2, minus 1, 3, minus 3, 0, and then 3, minus 2, and minus 2. And what we're going to do is we're going to multiply our matrix A times our vector v, and that's given us 3, minus 2, 1. Let's begin by taking our first row and multiplying it by our vector v. This is going to give us a minus 12, minus 6, plus 3. And now we're going to look at our second row and multiply it by our vector v. And we get a 6, plus 6, minus 2. And now we can look at our last row and we'll multiply that by our vector v. And we get a minus 3, plus 0, minus 2. Now we can go ahead and let's add this up. We have a minus 18 plus 3 is a minus 15, and then a 12 minus 2 is a 10, and then we get a minus 5. So what we have to determine if this is a multiple of our vector v. So we're going to put a little question mark here, set it equal to lambda, and then we're going to write down our vector v, 3 minus 2, 1. So let's see what this is. So we have a minus 15 is equal to 3 lambda. So that would be true if lambda is equal to minus 5. And then we have a 10 is equal to minus 2 lambda. And that again is going to be true if lambda is minus 5. And then lastly, we have a minus 5 is equal to lambda. And that's the same thing. Lambda is equal to minus 5. So this tells us that the answer to our question is yes, v is an eigenvector of our matrix A, and we can say that our eigenvalue lambda is equal to minus 5. In this question, we're asked to find the eigenvalues of this given matrix, and it's a 2 by 2 matrix. We're going to solve this problem by solving the equation determinant of A minus lambda I is equal to 0 for lambda. And then lambda is going to be our eigenvalues. Let's go ahead and set this up. Let's first compute A minus lambda I. That's going to be our matrix 4, 2, minus 1, 1, and then we're going to subtract off lambda times our identity matrix. And this is going to give us 4 minus lambda, minus 1, 2, and then a 1 minus lambda. So that's A minus lambda I. Now what we're going to do is find the determinant of that matrix, and we're going to set that determinant equal to 0. So we have the determinant 4 minus lambda, minus 1, 2, 1 minus lambda. We can indicate the determinant by just drawing a straight line, and we're going to set that equal to 0. Now, to evaluate the determinant, what we're going to do is we're going to multiply the main diagonal, and then we're going to subtract off the off diagonal. So this is going to give us 4 minus lambda times 1 minus lambda minus a minus 1 times a 2, and that's equal to 0. Let's go ahead and multiply this out. we're going to get a lambda squared minus lambda minus 4 lambda plus 4, and then we have a plus 2. Let's combine like terms. So we have lambda squared minus 5 lambda plus 6 is equal to 0. Now what we have to do is factor this. Notice that we have a 5, and the multiple of 6 is 3 and 2. So we can factor this as lambda minus 3, and then lambda minus 2 is equal to 0. So this gives us lambda minus 3 is equal to 0. And from there, we get that we have an eigenvalue lambda is equal to 3. And then we can set lambda minus 2 equal to 0. And we get an eigenvalue lambda is equal to 2. So our eigenvalues of our matrix are 3 and 2. In this problem, we're given a matrix A, and it's a 3 by 3 matrix, and we're asked to find two things. We're asked to find the eigenvalues of this matrix, and then we're asked to find a basis and geometric description for each eigenspace of matrix A. Let me tell you exactly how we're going to do this. To find the eigenvalues, we're going to solve the equation determinant A minus lambda I is equal to 0 for our eigenvalue lambda. To find the eigenspaces, we're going to put A minus lambda I in a matrix and augment it with 0, and then we're going to put that matrix in reduced echelon form and find X for each lambda. That's going to take a little bit of time. Let's go ahead and let's start by finding the eigenvalues. So for part A, we're going to start by taking determinant A minus lambda I equal to 0. We have the determinant of 6 minus lambda minus 2, 2. So we're basically just subtracting lambda off the main diagonal. That's what it means when we have A minus lambda I. And then we have a 3, a minus 3, and 7 minus lambda. And we're going to set that equal to 0. We're going to solve this by using cofactor expansion. I think that's the easiest because notice that in our second column, we only have one entry. So it won't take too much time to do this. Let's go ahead and let's circle this because that's our non-zero entry. So to find the value of this determinant, we're going to have a sign factor times this entry times what remains when we cross out the row and column common to that entry. So let's do our sign factor first. Our sign factor is a plus. You start in the upper left-hand corner, and then you work your way over, plus, minus, plus. We could have gone down and then over, and we would have gotten the same thing. The sign pattern just alternates with plus and minus. So our determinant is equal to plus times 4 minus lambda times the 2 by 2 determinant that's left, and that's a 6 minus lambda, a 3, a 2, and a 7 minus lambda, and we're going to set that equal to 0. So we have 4 minus lambda, and then in this determinant, we're going to evaluate the determinant by multiplying the main diagonal and subtracting off the off diagonal. So this is going to give us 6 minus lambda times 7 minus lambda minus 2 times 3, which is 6. I always tell my students, when you get to this point, you have to be very, very careful not to just start multiplying everything out. Because if you do that, you're going to end up with a cubic equation that's going to be really hard to factor. So what you want to do instead is just put this in your pocket for a minute, and then let's work on simplifying this part. So we have a 4 minus lambda, and then in this middle part, we're going to have a lambda squared minus a 7 lambda minus a 6 lambda, so that's a minus 13 lambda. And then we have a 42 minus a 6, and that's equal to 0. So we're going to simplify that inside, and we end up with a lambda squared minus 13 lambda, and then a 42 minus 6 gives us a 36. Notice that 4 times 9 is 36, and that also adds to 13, so we can easily factor this as lambda minus 9, and then a lambda minus 4. And see what happened by holding on to this term, we ended up factoring the entire cubic equation. This gives us eigenvalues of lambda is 9 and 4 and 4. Sometimes you can also write this as lambda is equal to 9, 4, and then in parentheses, you can write down multiplicity 2. Either way is usually fine. Okay, so let's go back up. We found the eigenvalues of matrix A. So let's go ahead and let's highlight these. We have 9, 4, and 4. Now what we have to do is find a basis and geometric description for each eigenspace of matrix A. I'm going to start by finding the basis associated with our eigenvalue lambda is equal to 4. So what we're going to do is we're going to take A minus lambda I, we're going to augment it with 0, and we're going to put it all the way down to reduced echelon form. So let's go ahead and do that. What we're going to do is we're going to have our matrix A, and we're going to subtract 4 off the main diagonal. So let me go back up here and we'll highlight this. There's our main diagonal. So we're going to subtract 4 off it. So we get a 2 minus 2, 2, 0, 0, 0, and then a 3, a minus 3, and a 3. Let's write that down. We have a 2, a minus 2, and a 2. We have a column of zeros, and then a 3, a minus 3, and a 3, and we're going to augment it with 0. Let's go ahead and circle our first pivot, and this is really nice. Notice that our second row and our third row are multiples of our first row, so those rows are just going to go to 0, and we can do a scaling on our first row and divide it by 2, so we get this matrix, 1, 0, 3 halves, augmented with 0, and then everything else is equal to 0, which is quite nice. Now, to find our eigenvector, we're going to circle our pivot, and we're going to solve for that pivot. So this is x1 plus 3 halves x3 is 0, which gives us that x1 is minus 3 halves times x3. Let's go ahead and let's form our vector x. There are 3 columns in A, so we have 3 entries in X. So we have X1, X2, X3. And then let's plug in. We have X1 is minus 3 halves X3. And now we have to figure out what to do with X2 and X3. Let me make a note up here that because these columns are missing a pivot, that means that X2 and X3 are free variables. So when you put them into your matrix, they just go in as themselves. So this is an X2 and that's an X3. Now what we have to do is split our vector apart. We can pull out an X2 and that's going to multiply 0, 1, 0. And then we'll pull out an X3. And for that one, we're going to have a minus 3 halves, a 0, and a 1. And our question asks us to find a basis for the eigenspace. So the basis is going to contain these 2 vectors. And I'm looking for some free space. Let's see if we can squish it down here. So let's just write down basis equals It's going to contain our first vector, 0, 1, 0, and then our second vector, minus 3 halves, 0, and 1. And that's the basis for the eigenspace corresponding to our eigenvalue lambda is equal to 4. Now, let's think about the geometric description. We have 2 vectors in it, so that means it's going to be a plane, and each vector is an element of R3. So our geometric description of our basis is that it's a plane in R3. Okay, we got that one done. Now I'm going to flip the page, and we're going to find the eigenspace corresponding to our eigenvalue lambda is equal to 9. I went ahead and I wrote down our matrix A just so we wouldn't have to flip back and forth between pages. So let's write down lambda is equal to 9. And we're going to begin just like we did before. We're going to take A minus lambda I, and we're going to augment it with 0. So for this one, let me go ahead and let's highlight our diagonal. We are going to subtract 9 off of our diagonal. So we're going to get a minus 3, a minus 2, and a 2, and then a 0. 4 minus 9 is a minus 5, and then a 0, and then a 3, minus 3, and then 7 minus 9, which is a minus 2. This one is a little bit harder than the other one to simplify. Okay, so the first thing I would like to do is do some scaling because I'm looking at this row, and we can make those a lot simpler. So I'm going to take row 1, and I'm going to change it to row 1 divided by minus 3. That's just doing a scaling. And then row 3, we're going to let be row 3 divided by 2. And this is going to give us a 1, 0, minus 1 on our first row. Our second row is going to stay the same. And then our last row is going to be a 1, 0, minus 1. Let me change that 0. It looked like a 6. There we go. Now we're all set. Let's go ahead and let's circle our first pivot, and we're going to proceed to get a 0 below that. All those entries are going to become 0. So we're going to take row 2, and we're going to replace it with row 2 plus 2 times row 1. And then we're going to take row 3, and we're going to replace it with row 3 minus row 1. Give ourselves a little bit more space. And here's what we get. The first row stays the same. And then we're going to multiply our top row by 2 and add it to our second row. So we're going to pick up a 0. The minus 5 stays. And then we're going to have a minus 2 minus 3 gives us a minus 5 and then a 0. And then we're going to take minus 1 times our first row and add it to our third row. So we get a 0, 0. And then we have a 1 minus 1, which is 0. Oh, that's nice. That row is all zeros. So we're almost done. Let's go ahead and let's circle our pivot here. To put our matrix in reduced echelon form, all of our pivots have to equal 1. So we're just going to take row 2, and we're going to replace it with row 2 divided by minus 5. Our top row is 1, 0, minus 1, augmented with 0. And then we have a 0, 1, 1, 0, and then our last row is zeros. So our matrix is now in reduced echelon form. I'm going to circle the pivots because those are the variables that we're going to solve for. We have x1 minus x3 is 0. So that tells us that x1 is equal to x3. And then we have x2 plus x3 is 0. So that tells us that x2 is equal to minus x3. And then let's just make a note that x3 is a free variable because there's no pivot in that column. Now we're going to form our vector x. It's equal to x1, x2, and x3. We're going to plug in what we just got for x1 and x2. So we have an x3, a minus x3, and another x3. And let's pull the x3 out front. And we get a vector 1, minus 1, 1. So our basis for our eigenspace corresponding to our eigenvalue lambda is equal to 9 contains the vector 1, minus 1, 1. And then lastly, let's talk about the geometric description. Our basis contains one vector, so our geometric description of our basis is that it's going to be a line, and our vector is an element of R3, so we're going to have a line in R3. In this problem, we're given that we have a 3 by 3 matrix A, and it has eigenvalues 1, 2, and 5. In part A, we're asked to find the eigenvalues of A transpose, A inverse, and A cubed. And in part B, we're asked to find the determinant of matrix A. Let's go ahead and let's do part A first. I want to begin by saying that the eigenvalues of a matrix transposed are the same as the eigenvalues of the matrix. So let's just write down the eigenvalues of A transpose are the eigenvalues of our matrix A. So our eigenvalues are going to equal 1, 2, and 5, just like matrix A. Now let's find the eigenvalues of A inverse. The eigenvalues of the inverse of a matrix are 1 divided by the eigenvalues of our matrix A. So the eigenvalues of A inverse are going to be 1 over 1, which is 1, 1 over 2, which is 1/2, and then 1 over 5, which is 1/5. Now let's look at the eigenvalues of A cubed. The eigenvalues of A cubed are going to be the eigenvalues of A cubed. So let's see. We're going to have a 1 cubed, which is 1. We're going to have a 2 cubed, which is 8. And then we're going to have a 5 cubed, which is 125. So the eigenvalues of A cubed are 1, 8, and 125. Now let's find part B. We want to find the determinant of matrix A. So the determinant of a matrix is the product of the eigenvalues of the matrix. So our answer is going to be, we're going to multiply our eigenvalues 1, 2, and 5, and we're going to get 10. So the determinant of our matrix is equal to 10. In this problem, we're asked to determine if the following matrices are diagonalizable. I'm going to start by telling you how you can determine if a matrix is diagonalizable. A matrix is going to be diagonalizable if either of the following are true. The first one says that our matrix has n distinct eigenvalues, and the second one says that the matrix has n linearly independent eigenvectors. So if a matrix has n distinct eigenvalues, it's diagonalizable. And if a matrix has n linearly independent eigenvectors, it is also diagonalizable. Let's go ahead and let's look at our first example. I'm going to write down that our matrix is equal to 4, 2, 0, minus 1. Notice that this matrix is an upper triangular matrix. There's a theorem that says that if a matrix is a triangular matrix, the eigenvalues are just the entries along the main diagonal. So we can write down that the eigenvalues of this matrix are 4 and -1. These are two distinct eigenvalues, so that tells us that our matrix is diagonalizable. Now let's look at our second matrix. This matrix is equal to 4, 3, 0, 4. It's also an upper triangular matrix, so the eigenvalues are the entries along the diagonal, and we can write down that lambda is equal to 4 and 4. In this matrix, we do not have two distinct eigenvalues, so our matrix may or may not be diagonalizable. What we're going to have to do is do a little bit more work and find out if we have or in this case, because it's a 2 by 2 matrix, if we have two linearly independent eigenvectors. What we're going to have to do is find the number of eigenvectors. To find the eigenvectors, we're going to take A minus lambda I, we're going to augment it with 0, and unfortunately, we're going to have to put this all the way down in reduced echelon form. Let's go ahead and let's do this. We're going to subtract our eigenvalue 4 off the main diagonal, so we get a 0, 3, 0, 0. So this is actually not bad at all. I'm going to look at this pivot, and let's go ahead and let's make that a 1. So our matrix is 0, 1, 0, 0, 0, 0. And there is our pivot. So this tells us, if we solve for this pivot, that we have x2 is equal to 0. And notice that our first column is missing a pivot, so that tells us that x1 is a free variable. So we have one free variable, so our x can be written as 0 times x1, and we can pull out the x1 and write this as 0, 1. So our goal was to find out the number of eigenvectors that we have, and we ended up with one linearly independent eigenvector. But for our matrix to be diagonalizable, we needed 2. So we can say that our matrix is not diagonalizable. Before we end, I want to make one note. Notice that we had one free variable. The number of free variables is going to be equal to the number of eigenvectors. So up here, when we found that we had a free variable and we only had one, we actually could have stopped and we didn't need to really find x, because just having one free variable will tell us that we just had one eigenvector and not two, so our matrix was not diagonalizable. In this problem, we're told that a matrix A is equal to P times D times P inverse, where P and D are given below. We're asked to compute A cubed. In order to solve this problem, we have to know a formula. Since A is equal to PD times P inverse, we can say that A cubed is equal to P times D cubed times P inverse. Notice that D is a diagonal matrix, so it's really easy to find D cubed. The hardest part of this problem is just doing the matrix multiplication. Here we go. Let's write down A cubed, and we're going to write down P, 1, 2, 3, 5. And then we're going to write down D cubed. So the way that you raise a diagonal matrix to a power is that you raise each of the entries along the diagonal to that power. So this becomes 3 cubed, 0, 0, and then 1 cubed. And then we have P inverse, which we're just going to write like this for now, and then we'll have to calculate it. So we'll just put a little -1 there to indicate that we need to find the inverse. We're going to recopy our P, 1, 2, 3, 5. And then let's go ahead and multiply out our d cubed. So this just becomes 3 cubed, which is a 27, 0, 0, 1. And then let's go ahead and let's find the inverse. So to find the inverse, we're going to take 1 divided by the determinant. So the determinant is the main diagonal entries multiplied minus the off diagonal entries multiplied. So this is going to be a 5 minus 6. And then we have to come up with the other part of the inverse. So what's going to happen with this part is that the entries along the main diagonal switch. So that's a 5 and a 1. And then the off diagonal entries in pink are going to get a negative. So let's go ahead and let's rewrite this one more time, and then we'll start our multiplication. So we have a 1, 2, 3, 5. And then we have a 27, a 0, a 0, and a 1. And then this right here is a negative 1. So in our matrix on the right, every entry gets multiplied by a negative. And this gives us a minus 5, a 2, a 3, and a minus 1. Now we can go ahead and we can start multiplying. I'm going to multiply these two first. We're going to start by taking this row, multiplying it by that column. So that's just going to be a 27. And now we're going to go ahead and multiply by this column. So that's going to be a 1 times 0 is 0, and then a 2. Now we can go down and multiply by our bottom row. This one's going to be a little bit harder. We have 3 times 27, so that's an 81 plus 5 times 0 is 0. So that's just an 81. And then we'll multiply our last one. So we're going to take this times that. So we get a 0, and then we get a 5 times 1 is 5. So that wasn't too bad. Now we're going to multiply by our P inverse. So that's minus 5, 3, 2, minus 1. So our first entry in the upper left is going to be a 27 times minus 5, which is minus 135, plus 2 times 3 is 6. And then in the upper right, we're going to have a 27 times 2, which is a 54. And then we're going to minus 2. And in the lower left, it's going to be, let's see, 400 and then 5. So that's going to be minus 405 plus 15. And then we're going to have a 162 minus 5. I always tell my students, don't try to do too much in your head. It's okay to write out extra steps. Now we're going to take 135 minus 135 and add 6. So that's minus 129. And then on the right, we get a 52. And then in the lower left, we have a minus 390. And then in the lower right, we have 157. And I'm going to highlight this because this is our final answer. That's what a cubed is equal to. In this problem, we're going to diagonalize the following matrix A. To diagonalize a matrix, what we have to do is write the matrix as A is equal to P times D times P inverse. Sometimes you'll only be asked to find P and D, but if it's not specified, then you actually have to find P times D times P inverse. Our first step is going to be to find D. Our matrix D is a diagonal matrix that contains the eigenvalues of matrix A. Then we're going to find matrix P, and our matrix P contains the eigenvectors of matrix A. And then lastly, we'll just compute P inverse, and then we'll write all three of them side by side. Let's start by finding D. What we're going to have to do is find the eigenvalues of our matrix. So we have the formula to find eigenvalues, determinant A minus lambda I is equal to 0. We're going to take our matrix A and we're going to subtract lambda off the main diagonal. and we're going to set that equal to 0. This gives us a 5 minus lambda times a 3 minus lambda. We're just multiplying the main diagonal, and then we subtract off the off diagonal, which is 2 times 4 is 8, and we set that equal to 0. Multiplying this out, we're going to get a lambda squared. We have a minus 3 lambda minus 5 lambda plus 15 minus 8. Combining like terms, we get lambda squared minus 8 lambda, and then 15 minus 8 is a 7, so plus 7. Give us a little bit more space. We can then factor this. We have lambda minus 7 and lambda minus 1 is equal to 0. So that gives us our eigenvalues. Lambda is equal to 7 and 1. At this point, let's go ahead and write down our matrix D so we don't have to come back later and think about it again. So our matrix D is a diagonal matrix that contains the eigenvalues along the diagonal of D, and all the other entries are 0. So I'm going to put a 7 and a 1 along the diagonal, and then the other entries we're going to set equal to 0. Now let's go ahead and let's find P. So to find P for each lambda, we're going to have to find the eigenvector. I'm going to begin with lambda is equal to 7, just because I wrote that one first. And what we're going to do is we're going to take a minus lambda I, and we're going to augment it with 0, and we're going to have to put it all the way down in reduced echelon form. So let's see, our matrix A, we're going to have to look back up. 5, 4, 2, 3. So we're going to have a 5 minus 7, a 4, a 2, and then a 3 minus 7. And we have zeros. Let's see what this is equal to. This is going to be a minus 2, a 4, a 2, and then a minus 4. Oh, that's nice. Our second row is a multiple of our first row. So let me highlight that. That row is a multiple of our first row, so that row is going to go to 0. And then let's do some scaling on our first row. And let's take row 1, and let's replace it with row 1 divided by negative 2. And the reason we're going to do that is it's going to give us a 1 as our pivot. So we have a 1, a minus 2, and a 0, and then our bottom row goes to 0. We mark that as a 0. We can now solve for x1. That's our pivot variable. So we can say that x1 is equal to 2x2, and that tells us that our vector x, which is x1, x2, is equal to plugging in for x1, 2x2, and then x2, and we can pull out an x2, and that becomes our vector 2, 1. What we have to do now is pick a value for x2 so that we can find an eigenvector. I'm just going to let this be equal to 1 and make things really easy. So our eigenvector is going to be equal to 2, 1. We're going to have to put that in our pocket for a minute, and we'll come back to that after we find our other eigenvector. So now we're going to let lambda equal 1, and we're going to do a minus lambda I again. Let's go all the way back up here. 5, 4, 2, 3. So 5 minus 1 is 4. And then we have a 4, a 2, and then 3 minus 1 gives us a 2. And you can see that our second row is a multiple of our first row. And we can go ahead and scale our first row by 4. And we end up with 1, 1, 0, and then a row of zeros. Let's circle our pivot, and we can solve for x1. So we see that x1 is minus x2. So our vector x is equal to x1, x2. And then we'll plug in x1 is minus x2. And then we'll pull our x2 out, see if we can squish it in here, and we get minus 1, 1. Again, I'm just going to make things easy, and I'm going to choose this vector to be equal to 1. You could also have picked it to be minus 1. It doesn't really matter. And so our eigenvector is going to be minus 1, 1. Now we can go ahead and write down our P matrix. So the only thing that we have to be really careful about is, let's go back up to D. Do you see that 7 is in our first column? So that means the eigenvector corresponding to our eigenvalue of 7 also has to be in the first column. So that's this one right here, and we have to put that in our first column. So 2, 1, and then the other one goes in our second column. Now our third step is to find P inverse. So P inverse is going to be 1 divided by the determinant of P, which is the main diagonal 2 minus the off diagonal, which is negative 1. And then inside, our main diagonal entries switch, and our off diagonal entries get a negative. So notice that this is equal to 3. So every entry is going to be divided by 3. We can now write down our final answer. So our final answer is matrix A is equal to our matrix P, 2 minus 1, 1, 1, times our matrix D, which was 7, 0, 0, 1, times our P inverse, which we just found to be 1/3, 1/3, minus 1/3, and 2/3. Be sure to check out the next review video on orthogonality and least squares. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.